The world of machine learning did not expect what was about to happen after the 20th of September 2019 by a shocking statement made by a prominent researcher in deep learning, Jürgen Schmidhuber. Stop crediting the wrong people for inventions made by others. The reference was, of course, to the famous, or rather infamous, Honda Prize in 2019. The award's recipient was another prominent figure in the machine learning world, Geoffrey Hinton, for inventing the backpropagation algorithm in deep learning for artificial intelligence, and for his other contributions in the field, including contributions to distributed representation and speech recognition. Hinton went on to be known as the godfather of AI, something that didn't settle with Schmidhuber very well, as he wrote a furious critique of the Honda Prize, stressing that Hinton did not invent the backpropagation algorithm, but Seppo-Linoimo did in 1970. This was, of course, followed by a response by Hinton emphasizing that he did not claim to have invented backpropagation, but that he only showed how it works, which, by the way, begs the question, why then did he receive the Honda Prize for it without any objection, and why didn't he and his co-authors cite the previous contributors to backpropagation in the research paper Learning Representations by Backpropagating Errors? This heated series of arguments continued for some time in what came to be known as one of the most followed drama series in the field of AI. But you might ask, so what? Who cares who was the inventor of backpropagation as long as we get to use it? There's a long answer about research ethics and intellectual property that I will not get into here. But the short answer is that backpropagation is the actual part of learning in machine learning, and what makes AI systems learn from their errors and be able to accurately respond or predict. The main reason that for many years these contributions have not been talked about so much in the mainstream media was that we didn't have powerful enough hardware to be able to tap into the vast potential of algorithms such as backpropagation, something that has definitely changed recently as you witness the surge in AI-related research and apps. And quite frankly, you won't be able to progress in the field of AI unless you learn not just the concept of backpropagation, but also how it operates. And I mean how exactly it works. And your journey starts with understanding a simple neural network design or feedforward neural network and the journey of the input, for example, a sequence of words through each layer's nodes, till the last layer or the output layer, where the next word in the sequence is predicted. The input can be anything such as a sequence of words, pixels in an image, audio signals, and so on, which are denoted by x1 to xn, where x1 is the first input unit and xn is the last one. Each input is represented by a unique numerical value in an embedding process. As the input enters the system, they are first assigned a random weight and a bias term. The weight is a value which shows the importance we give to each unit of input data. The weights are multiplied by each input data. The weighted sum of these inputs plus the bias term then travel to each node of the first hidden layer. The hidden layers are the layers where the main calculations in a neural network happen, and you can think of each node as a place for an activation function. So what is an activation function and how does it work? The short answer is that they are nonlinear mathematical functions that can learn nonlinear patterns in the data, which is the main reason we are interested in using a neural network instead of, let's say, a simple linear regression. In a linear regression problem, there is a linear relationship between your variables. For example, predicting your school grade based on the number of hours you studied. So essentially in linear regression, we can simply fit a straight line through the data points to find the best model that represents this relationship better. But what if we have a complex or nonlinear problem? For example, separating these classes of data points cannot be done by a simple straight line. To find complex patterns in the data, as you can see in this classification task, we need a nonlinear activation function, such as ReLU or even Sigmoid functions, that can neatly classify this circular and nonlinear shape of data points into two distinct categories. If you want me to make a more detailed video about this topic, Let me know in the comments. But for now, let's continue with our journey through the neural network layers. Remember that the output of an activation function is a numerical value too. These functions map the input often in the range of 0 to 1 or -1 to 1. The output is then taken as the input to the next layer's nodes, and this whole operation is repeated in all hidden layers until the feedforward paths come up with a predicted output. For example, what should be the next word in that sequence of words, or whether a text has a positive or negative sentiment. Now, here's where the cool thing happens. If the prediction is different from an expected output, the algorithm backpropagates the error through the network. The error or loss is the difference between the predicted word or clause and the expected word or clause in their numerical forms. If by now you're still not convinced that backpropagation is cool and what all that fuss for claiming who invented it was, keep listening. During the backpropagation, the network uses an algorithm called gradient descent, whose job is to find the most optimal values for the weights or importance given to each input data at each connection and device terms, so that the next time the network can predict the accurate output, or at least reduces the error or loss between what it predicts and what it should be. Without making this video essentially long, the gradient descent algorithm effectively moves these weight and bias parameters in the opposite direction of the gradients of the loss function until the gradient of the loss function approaches 0. At this point, where the loss or error is ideally 0 or very small, the weight value is ideal, because now we found how much importance in the numerical value we should give to each input data to minimize the error it contributes to the final prediction of the neural network. And surprise, surprise, we get a more accurate response. What this means is that because the gradients are in the direction of the increase of the loss or cost function, if we move the parameters in the opposite direction, we get smaller error values. Therefore, the cost function will give us a smaller value, and therefore we manage to reduce the gap between the previously incorrect output and the expected correct output. Voila! I just explained how the neural network and backpropagation work and the main ideas and operations behind them, of course as simplified as I could possibly make it. Mind you that a larger picture of what goes behind the scenes also includes understanding the math behind different activation functions, the chain rule different loss functions, and how the gradient descent algorithm finds the minimum of the loss function step by step and keeps a record of partial derivatives in our gradient vector in the forward pass and then readjusts the parameters in the backward pass. Believe me, there is a ton of stuff to unpack for future videos, but for now take a look at these machine learning papers and concepts that can get you ahead of 99% in AI.